Hi folks, so you're doing something called calculus. Okay, that's a massive topic, um, which consists of many parts. All you're going to look at is two topics that go under the heading of differentiation and integration. Like I said, these are like the kind of two branches, but there are other branches or subtopics here. Uh, like I said earlier, calculus is absolutely massive. You can liken it um, to an apple. Okay, so here's calculus. It's an apple, even though some people say calculus comes from the Latin word for pebble. Um, but don't try and bite that pebble. So, if calculus was an apple, see the people who strove to unlock the secrets of calculus, they didn't know about the whole apple. No, these very clever people, very clever people, Leibniz and Newton, two of note, they didn't get to see all that or hold that. They were very unlucky if they got a bite of it. And maybe not even a bite as big as that. See, most mathematicians, and they're lucky to get a close lick of calculus at Apple. I'm probably, I don't think I would even get a lick. Okay, I might get a drive-by or something of an apple. But see, for most people, they're lucky using their big massive telescope if they can actually see calculus up there in the heavens, somewhere out there in the cosmos. So, the moral of the story here is we're not really doing a lot of calculus, okay? So don't think after this you're a calculus expert. Even the person who's talking about this is not a calculus expert, which you may find apparent very soon. Anyway, let's go for it. Um, so they talk about the first one, differentiation. They're looking at things called rates of change. This phrase is going to appear quite a lot. So, rates of change. Well, well, we've only got two things here, and traditionally we use x and y. Think about a coordinate system here. Could be x, y, and z. Could be x, y, z, and t. Right, but we're going to stick to two variables here. How does one change compared to the other? Rates of change. Okay. You probably looked at this before without even thinking about it. A straight line. What's the rate of change with x the horizontal in relation to y the vertical? Uh, well, that's actually just the gradient. The gradient of the line, and you might have a definition for that there. Um, the change in y over the change in x, given any 2 points, x1, y1, x2, y2. So here, that's actually change in y over the change in x. That's fine. That's brilliant for a straight line. So coordinates of 2 points, you can put them in there and get change in y over the change in x. That's fine for a straight line, but what about the rate of change of the graph of this function here? Okay, well, what we're looking at is the steepness along the curve here. That's what we're looking at here. So we're talking about the rate of change of the gradient function. So I've just selected 3 points here, hope you can see them. And what I've done there is I've just put a line on at these points there. The lines, we refer to them as being tangential to the curve at those specific points here. And the gradient of the curve is actually equivalent to the gradient of the tangent lines here. That's what we're looking for along here. So, but unlike a constant straight line, it seems like the selected points on the curve, the gradients of the tangent lines, they look a little bit different. So we could just actually select one and maybe zoom in here. And then we zoom in, um, the curve in the tangent line, or the curve, it seems to look as if it's kind of straight here. That's what we're looking at there. It looks straight. So it looks like the curve and the line are very, very similar, almost straight. So we're going to talk about a thing called a derivative. Well, the derivative is the gradient function or rate of change. We've said, specified that rate of change is going to come into this quite a lot. So we're talking about the rate of change of the function. It's called the derived function or just the derivative. Okay, we've eventually got there. It's called the derivative. Okay. We saw earlier the M symbol we traditionally use for gradient when we're looking at straight lines. It's just a change in y over the change in x. That's what the little triangles represent, a change in. Okay. So for our curves, or where we'll have a function, maybe y equals something or other, what we're looking for is what they call the instantaneous rate of change. Because along a curve, as we saw earlier, sort of the steepness seems to change as it's going along it. That's what I'm looking for. So instead of delta y over delta x in those triangles, we just change it as dy over dx. This is just notation. We're just getting used to notation here. And it says where x and y are related, just like coordinates. How does x change as y changes here? Right, okay. So that dy over dx, that is enunciated or spoken as dy by dx. So if you hear me saying or someone else saying dy by dx, they're talking about the derivative or gradient function. Okay, let's go for the rules for differentiating. This is where you start paying attention. So we could have something like 7x squared. That's a certain type of function. That's a polynomial, whatever that is. And y equals sine x, that's a trigonometric function, whatever that is. And then there's another trigonometric function. So I think we're going to limit it to these. So polynomials and trigonometric functions. In fact, we could look at power functions as well, where the power doesn't always have to be what's called an integer, positive or negative whole numbers. Could be like -3/4 or something like that. That would be fine. But let's go for it. So here's the first type. Y equals ax to the n. That looks like 7x squared. Okay? So y equals ax to the n. All you're going to do is move numbers about, and which will mean in turn So that's the numbers, moving letters about, moving numbers about. Okay. So to get a derivative, dy by dx, take the power n, bring it down the front, multiply anything that's in front of x, i.e. a in this case. Don't touch x, but see the power n, or whatever symbol you're using for it, if it's a number, can you reduce it by 1? That is it. That's the power rule for differentiating polynomials or power functions. Right, that's it. Let's go and jump in for an example. So differentiate 5x cubed, 5x to the power 3 with respect to x. Okay, so according to that rule there, bring the power down the front. It multiplies anything in front of x and reduces the power by 1. So that 3 is a power, it comes down the front. Okay, dy by dx, that's the notation. It comes down the front, times the 5x. Can you reduce the power by 1? That's it. Let's tidy things up. 3 5 is 15, 3 take 1 is 2. That is your derivative. Later on, you'll be using this to evaluate things. You'll be actually determining a gradient function, which is a steepness or a rate of change. Okay, so you got 3 there. So why don't you pause this little video here and have a go at that? 9x to 7, 3x to 5, and 6x. Have you paused it? Right, good. If you did, let's come back in very quickly. 9x to 7. Bring the 7 down the front to multiply the 9. Keep the x here and reduce the power 7 by 1. Okay, 7's down the front, times the 9x, reduce the power with 1 and tidy up. 7, 9, 63, 7 together once, it's 6. That's you found the derivative of 9x7. You're just moving things about the page. 3x to 5, let's bring the 5 down in front of the 3. Leave x alone and subtract 1 from the power 5. Tidy up, 5 3s are 15, 5 take 1 is 4. That's your derivative. It's as easy as that. That is it. Initially, calculus is not difficult. Okay, y equals 6x. Well, this is a wee bit different. It doesn't appear to have a power, but actually the power is 1. The single x on its own is 1, or it has power 1. So it fits the template ax to the n. Bring the 1 down in front and multiply the 6 and reduce the power by 1. Okay, so that gives you 6x to the 0. You might think that's fine. Answer up the back of the book wouldn't be the same as that. So what you need to remember here, by using your laws of indices, that anytime that you've got x to the power 0, like it's showing you there, that's actually equivalent to 1. So x to the power 0 is 1. So that's going to be 6 times 1 there, which is just 6. So that's your derivative. Right, this is a special case when it's a number times x, or whatever the variable of choice is, i.e. the letter of choice. So what you need to go 6 times x. In future, all you do is all you do is read your script. Okay, but yeah, anyway, I'm going to, what is 6, y equals 6x. I might have asked you this in class and tortured you. What's a straight line? Okay, y equals mx plus c. I've got y equals 6x. Where's the plus c? Plus c is 0. That doesn't matter. But what we've got here, m is changing y of changing x. That is the derivative. So what we've got here is 6 is actually, yep, it's sitting in front of x. That's the gradient. That's actually the gradient there. That's what we've found. Right. It's a derivative. So when it's just y equals a number times x, if we're connecting y and x, just go straight to the answer. Just bump x. Okay. Bump it. get rid of it. Okay, now if you think this is going a little bit fast, you can always pause and go back. That's the whole point of these little videos here. So it looks like we've got a combination of three things here. Yep, 16x cubed, 9x squared, and 2x. Okay, so they all seem to fit the format of we'll get a rule. To differentiate each of them, apply the rule 16x cubed, bring the 3 down the front to multiply the 16, reduce the power by 1. Okay, do the same with 9x squared. That would be 2 times 9 is 18, reduce the power by 1, 2 take 1 is 1, x to the power 1, we just leave as x. And finally 2x, we saw that just like the 6x, its derivative is 2. Right, hopefully this is not too challenging. So hopefully we can see here what's happened here. I just want to go through it because I've showed you the answer as well as the question. So in the first one, if 4 comes down to multiply the 5, okay, that's how we get the 20. 4 take away the 1, that's how we get the 3. Okay, that's what happened there. Likewise, when we move on to the next one, bring the 3 down the front to multiply the -7. That's why we get -21. Then go back to the power, reduce it by 1. That's how we get the 2 there. And just moving on to the last term there of 9x. So that's just a number times x. And number times x, what happens here is we just bump the x. So hopefully, well, not hopefully, that is our derivative. Okay, right. Well, this one here, what's this? Differentiate y equals 3. There's not an x in sight. Right, so it has to fit the format. We need y equals ax to the n. So y equals 3 is 3 times 1. But hopefully you remember a few pages back that we express 1 in terms of x, which is x to 0. So now this fits the format ax to the n. Okay, so it looks like I brought the 0 down in the front to multiply the 3. That's what I've done there. Just remember the power here. The power always gets reduced by 1. We've done that there. Okay, and 0 times 3 is 0. X to 0 to the -1. That's just 0 because anything times 0 is just 0. Okay, right. I think it's taking me around the houses here, folks. Right, let me quickly zoom forward. I'm not stopping this video. Okay, I'm not stopping this. I'm trying to get this on board for your benefit. Right, y equals 3. Yep, moving through the motions. That's fine. That was your derivative. So see the top line, y equals 3. That's just a number, what we call a constant. Okay, so what you would do in future, just go from y equals 3, its derivative is 0. Okay, 0. So if it was y equals 17, its derivative would be 0 there. Right. So you don't, all these intermediate lines, miss all that stuff out. So y equals a number, its derivative is always 0. Okay. What about this one here? We've got again, we've got a combination. Have we got any special rules here? X squared. Yep, the 2 comes down the front. It would multiply it in front of x, technically. 2 times 1 is 2. Take 1 for the power. Again, 5x, that's a special case. Number times x, just bump x to get a derivative. And numbers on their own, their derivative is 0. That's what would happen there. So hopefully that's what you would get there. 2x plus 5. Right, okay. This one here, 3 over x to the power 5. Well, is it just going to be 3 over the 5 comes down the front, 5x to the 4? No, this does not fit the format. The format has to be 3 times an x to a power. So what we have to do here is bring x up next to the 3 or any other number that's there. And because we're bringing the x to the power up from the denominator, the bottom part of the fraction, we have to change the sign of the power. And you know, that's just using your laws of indices here. So we've done that there. That's fine. Okay. Now it looks like ax to the n. I know it says negative n in the little blue cloud, but that's just a bracket. Apply the rule. Bring the negative 5. Okay. Bring it down the front to multiply the 3, and remember to subtract 1 from the original power and then tidy up. Okay. There's that negative 5 come down, times the 3x, reduce the power by 1 and tidy up. Negative 5 times 3, negative 15. Negative 5 take away 1 is negative 6. That answer is absolutely perfect there. Perfect. Leave it like that. But if you look up a book, it might not say that. It does in here, you can take it further. So it's that x part there. Because it's got a negative power, they don't like that. So what they might tend to do is take that downstairs underneath the negative 15 and make the power positive, and they've dragged the negative out in front and level with the fraction bar. Right, okay, they're just changing the letters here. That doesn't matter, just to get used to things. Let's go to the base things here. Take the 5 down the front, 5 times 12. Take 1 for the power. Next one, take 2 down the front to multiply a negative 19 and take 1 for the power. And remember, constants without a letter, without a z, just get rid of that. And hopefully you will see that happening. Okay, yep, 5 12s are 60, 5 take 1 is 4, 2 times negative 19 is negative 38, lots of z, and derivative of a constant, i.e. negative 17, constant is a number on its own for us, so it looks like that's our derivative, and it's a change in w in relation to the change in z. Right, that's fine. Okay, here's one here. If you've got two terms here within the brackets, we need to multiply that out. I'm just going to go through this quite quickly here. You should be used to you should know how to multiply out brackets with different powers, that's fine. So here we go. That looks like I've multiplied out. Start with 2 things times 2 things, end up with 4 things. That seems correct. Looks like I've got a few things with x squared in the middle, so it's negative 2 add 5 is positive 3. So of x squared, add 3x squared, take away 10. Right, that's me just multiplied it out. We can't differentiate at this level with the rules we have available. Okay, So I'd have to take it there. Now I'm going to differentiate. So again, take the 4 down the front, multiply f in the front of x, and take 1. Same in the next one. Take the 2 down the front, that multiplies the 3, and reduce the power by 1. The end value is a constant, its derivative is 0, so you would just get rid of it. That's what we're going to do. Okay, there you go. 4 down the front, reduce the power by 1, that goes to 3, 4x cubed. Next one, 2 times 3 is 6, and 2 take 1 is 1. We don't need to show the 1 there. The negative 10, it's a constant number on its own. Get rid. Right. Here, for dividing top and bottom by the same time, 2x squared. So I'm just separating it out. 10 divided by 2 is 5. And the next one, 6 divided by 2 is 3. Use your laws of indices here. I'm not going to go through laws of indices. You should know that. You're now in the big school. That should give you that there. Okay. Any problems like that, go back and look at your notes on laws of indices. Right. The bottom line here is we can't, at our level, with a quotient fraction, they've not told us the rule. They haven't told us the rules yet. I don't know why it keeps coming back to that there. Let me see. Okay, we got to that there. Yep, 5x to the 4. We got it down to there. So the 4 comes down to multiply the 5 to give you 20. Reduce the power of 4x down to 3 because we're reducing it by 1. Take away the 3x. And remember, if it's just a number times x, bump the x. So it should take you to there. Right, this is going on and on, this lesson. Right, I'm going to let you look at that. I'm not going to talk through this one. Okay, I'm going to talk about notation now. If y is a function of x, they're connected. So y equals mx plus c. Y is a function of x. They're saying that y equals f in front of x in a little bracket. Well, the way that's enunciated is f of x. Okay. Y is a function of x. To get an answer for y, I need to know what the x number is. F is just relates to function. Function being a rule or a process. So we'll get different notation here for function and derivative. So if it's just y, we can write it as dy by dx. That's if x is the other variable. Or if we're using the function notation, f of x, what they tend to do is just put a little dash there to indicate they're differentiating. And sometimes this is called lazy notation. If it's just y, instead of writing dy by dx, we can just do what we did above with the f notation and just put in a little dash here. Okay. A little dash makes it tastier. Right, okay. I'm got the f notation here. The rules are the same, ax to the n. So that should become 3 times the 9, give me 27. 3 goes down to 2, 2x, get rid of x. It's a notation I'm interested in here. Make that f dash of x. 27x squared plus 2. Fine. So this is all about notation here. Differentiate 6x plus 7. I've got the y here. I can either use dy by dx or y dash. I'm using the Lazy notation y dash. 6x, that's just a number times x, that will become 6, and 7 is on its own, it gets bumped, its derivative is 0. That's my answer. Okay, y equals the square root of x. Square root, often referred to as a radical symbol. It's old-fashioned, we'll get rid of it. Oh, we hate it when they say remember. Square root of x is x to the half. That's your laws of indices again. So here we go. Exchange, get rid of the radical symbol or square root, whatever you want to call it. That's fine. That is ax to the n, 1x to the half. Apply the rule. Okay. Bring that. I'm using the lazy notation y dash. Half comes down the front. Don't touch x. It reduces the power by 1. That's fine. Power half take away 1 is negative half. That answer is perfect to there. You can leave it. But if you look up the back of a book, probably won't say that. So, like they're saying, we can take it further. So it's probably to do with the x having a negative power. So make that a positive power. Take the x downstairs next to the 2. Make it positive, and they might exchange the x to half into its old-fashioned notation of the square root of x. So that way 1 over 2 root x. Bingo! Right. There's a little exercise for you to do. You can do that in your own time. Because, as we keep saying, you can pause the video and look at how we're using 7, 8, and 9. Oh, they're using different letters to confuse you. Don't let them confuse you. Question 6, you need to multiply out the brackets there. Okay. Question 11, you need to multiply out the brackets. I won't tell you, I'll let you do them. Okay. Right, we're nearly there. The writing's very scratchy because I'm using this scratchy pen, which is a foot away, 30 centimetres approximately from my laptop. Here, looking at basic trig functions, so here we go. We're only going to be looking at sine and cosine, or variations on them. Y equals sine x, its derivative is simply cos x. That's it. You may have a multiple, i.e. a number in front of sine x or cos x, that's fine. Just apply the rule and carry that number along in the front. So sine goes to cosine, so dy by dx, which is 3 cos x. That's it. Nothing else. Okay, 27 sine x. I know sine x goes to cos x, so 27 is just going to come along for the ride. That's it. Its derivative dy by dx is 27 cos x. Okay, y equals cos x. That's our other basic trig function. We dealt with sine x. Now we're dealing with cos x. Its derivative is actually negative sine x. Somebody clever's thought it up. They told me, I'm telling you. Okay. Right. And again, if it's a multiple of cos x, the multiple, i.e. the number in front of the cosine, would go in front of the sine part with the negative. So if it's 4 cos x, if 4 comes along for the ride, when we differentiate it, cos goes to negative, and after the 4 we'll have sine x. That is it. Okay, nothing to get excited about here. That is it. So, I'm just going to tidy up this one. This looks as if I've not tidied it up completely. Just so you can see, I've got negative 5 cos x, so watch out when they put negatives in front. But the thing is here, with cosine, we know it goes to negative sine. So that's why in this part here, I'm just bringing down the negative 5. Okay, so that's a negative 5 from here. Right, so what's happening next? I know that cosine goes to negative sine x, but the negative will appear in the front initially, then the sine x after it. Okay, then we'll sort out that negative, negative business there. Going to sort that out. So negative, negative, they're really multiplying. So we got positive, we can release the bracket and just get 5 sine x. That looks okay. Right, here, sometimes we have actually got values in front of x. That's um, what we refer to as a multiple angle here. So it's an angle other than just single x. The rules are kind of similar here, but this time I'm showing you there's actually a number in front of sine as well. We're calling it a. So when we differentiate here, see the number in front of x? Can you bring that out the front? Multiply anything in the front of sine. We're referring it to a. Sine becomes cosine, positive. And see that bx part? It stays the same. That's the rule. That is it. All you're doing is moving numbers about the page. Right. Okay. 4 sine 3x. Right, I've got a multiple here. I've got 3x. So I need to, when I differentiate, I know that number in front of x comes out the front, multiplies anything in front of the sine part. So that's going to be 3 times the 4. Sine goes to positive cosine, and the 3x part stays the same. Tidy up the 3 times 4 at the front. Okay, going to 12 cos, and the 3x stays the same. That is it. Right, nearly there, nearly home dry. So we'll now get a number times cos, a number times x. So let's get its derivative. And cosine, if you remember, it went to negative. So, but bring out the b again. It comes out the front. It multiplies anything there. Yeah, that's what we've done there. There's b times a or a times b. But also remember, cosines go to negative sine. So that's why I put that in there. And whatever's after the sine or cosine part there, that will just be replicated there. Okay, that's it. That's the rule. We're just moving numbers or letters about the page here, doing a little bit of simplification. Right, 8 cos 5x. Okay, so it looks like bring the 5 out of the front. You know that when you differentiate cosine, it goes to negative. That's why we're going to have that there. And cos goes to sine, and the 5x will stay the same. Right, so I'll just go through that there. Yep, got a negative. But 5 comes out, times 8, cos goes to sine, and the 5x part stays the same. Do negative 5 times 8, negative 40, going off sine 5x. That's it, folks. I keep saying, we're just moving things about the page here, doing a little bit of arithmetic. That is it. You will have the rules in front of you. Okay, so that looks like we're home and dry here. There you go. Forget that. Right. So that was very, very well, it wasn't brief here. That was nearly 40 minutes. But just remember what we said about calculus. We kind of sort of looked at differentiation, and just remember what I said. As a big calculus apple, the clever people took a massive bite out of it. The less clever people, which I'm probably not even included in, we were lucky if we got a lick of it, or even caressed it in some kind of way, and you're lucky if they even let you see it. In fact, oh, it's getting smaller and smaller. Look how small wee calculus apple's getting. So, but you never know. You never know. They might make it a wee bit bigger for you. Okay. Right, so I'm going to leave it there, folks. Okay. I'll say again, you're just moving numbers about the page. Okay, so I'm going to leave it. Right, bye for now. Bye.